All right, so we've been looking at reactions. Let's take a minute and start to talk about some of our properties that then are created when we start to look at our different molecules and compounds that are formed. Going to be a fair bit of review here as well, just to kind of refresh some of our different chemical properties and chemical bonding. Just want to make sure we're doing okay as we continue to kind of move forward and kind of dig into our what we call colligative properties, which is really where we're going for this unit. So just as a reminder, there's kind of two types of attractions or forces that we can start to see within our actual physical molecules. And the first ones here are all about within the molecule. We call those intramolecular reactions or intramolecular forces. They're within. So if you're an introvert, you keep things to yourself within. Intramolecular forces would be like your bonds, your ionic, covalent, and metallic bonds. For an ionic bond, you actually have to have a full transfer of electrons from cation to anion. And then as a result, we have this attraction that then pulls our ions together to form our ionic compounds. For our covalent intramolecular, we've got two different atoms that come together that then share a pair of electrons between them. As a result, we now have kind of these shared orbitals. Ooh, we can talk about hybridization and Lewis structure. These are all going to be important when we start to look at our covalent molecules, the sharing of two electrons between two nonmetals. And for our metallic substances, we know these are delocalized electrons, kind of lose the outer electrons. They're now freely moving throughout the metallic substance. That's why we've got such great conductivity and ductility and malleability within our metallic substances. So these are all within. Our intermolecular forces are a little trickier. Probably the most relevant or most prevalent, the most common is our hydrogen bonding or our surface tension of water. This is the one that you all know. That's between two different water molecules. That's an intramolecular force between our molecules. And so when we talk about intermolecular forces, interstates go between states. Intermolecular forces are between molecules. And so there's a couple of different types of these that are worth noting. And so some of these you've seen, I believe in college chem, we kind of covered the big three, our hydrogen bonding, dipole-dipole, and our LDF, our London dispersion force. But there are some others that we should be familiar with. And when we start to look at these intermolecular forces, a lot of it comes back to the structure of the molecule or of our substance. Let me grab real quick. If you remember, this comes back to our kind of Lewis structures and how we've gone about building in three-dimensional space the molecules and their electronegativities. So for example, here we've got three different atoms, A, B, and C, each with slightly different electronegativities. If we look right now, B, our atom B has the highest electronegativity. We're saying that A and C are lower on the electronegativity scale. So if we're thinking about electronegativity, that's the degree of attraction for the electrons. Between A and B, the electrons are getting pulled towards B. Between C and B, the electrons are getting pulled towards B. And so if we're talking about the bond dipoles, where's our charge distribution? Where are the electrons getting pulled? They're getting pulled towards kind of the B atom in our molecule. Remember, though, that those electrons are negative. So now we have this region, this area around B that's more negative than what we had at A and C. A and C have lost some electrons, not completely, but pulled away, so they're now a little bit more positive. If we were to look at our electric field, not what I wanted space filling. I can't do that with my current Java. If we're looking in three-dimensional space then, if we were going to compare the whole molecule then, we would say that the top side is more negative and the bottom side is more positive. And this is what we see with water. Water being the prime example here. This side is a little negative, the bottom is a little positive. We would call it a polar molecule. It has two poles. As a result, now it's going to have specific properties or certain attractions to other molecules that can have intermolecular forces. And so we got to remember when we start to do this that it really is dependent on the shape, the Lewis structure, and how we start to build the models. We'll talk more about that as we start to kind of work in. Today we're just talking about kind of the various intermolecular forces. And so if we look at our different examples, an ion dipole, the best analogy or the best kind of example of this is why salt dissolves into water. Our salt crystal is very much an ion. This is our chloride ion. It's slightly larger. It's got a negative charge. Our sodium ion, let me grab one here, smaller because it's lost its outer shell. This is our positive ion. And if we think about our water molecules then, our water molecules, we just said that the oxygen side becomes a little bit negative. The hydrogen side becomes a little bit positive. If this ion is positive, it's going to attract to that negative oxygen. It's going to get stuck. And this is why when you throw this salt into a big beaker of water, our sodium ions actually dissociate. They get pulled away. What ends up happening is all of our waters kind of line up so that their oxygen sides are close to that positive, and then they float away. They dissociate away into solution. And then at the same time, more water molecules come in, and the positive hydrogens click on to that chloride and kind of surround that chloride. Just, I like to think about the linemen in the huddle, kind of huddling around their quarterback. And then the positives all line up and pull the chloride away. And this is what we would call this attraction. Very nice, satisfying click. That attraction would be an ion dipole force between one ion, an ionic substance, and a polar molecule. A polar molecule. Our second example would be hydrogen bonding. Hydrogen bonding, remember, has to have kind of specific bonds. You got to have a hydrogen bonded to either nitrogen, oxygen, or fluorine. We sometimes say it's NOF or FON because chemistry is fun. Chemistry is fun. What ends up happening here? We got two water molecules, right? Oxygen side is a little negative, hydrogen side is a little positive. Because these are polar molecules, they line up to attract to one another. And this is why water has surface tension. It is this attraction. And I wish I had a time machine. It does bother me a little bit that they call it hydrogen bonding, even though it's an attraction. This hydrogen isn't actually bonding to this oxygen. It's just kind of loosely held there, just kind of attracting to that oxygen. This is the hydrogen bonding, not the actual bond within the molecule. That would be covalent. That's a polar covalent bond. Hydrogen bonding here then is, lost my hydrogen or my water. Hydrogen bonding is here between. This would happen also if we had, for example, ammonia. So this is NH3. We've got two electrons here. It's a trigonal pyramidal shape. Ooh, the shapes. We've got four regions of electrons. The lone pair aren't shown here, so we'd say it's sp3 hybridized. Ooh, boy, been a while. And so we would say this is trigonal pyramidal. As a result, if you had two of these, there would be an attraction between those. And so we would say that there's some hydrogen bonding occurring between them. Dipole-dipole, that's just two poles, right? So if I had, for example, a diatomic element or diatomic compound, halogen and a hydrogen, the halogen's more electronegative. Remember, electronegativity increases as we head towards fluorine. Fluorine has the highest electronegativity. Because the hydrogen's a little bit positive, on another molecule, this is a little bit negative. We'll end up with an attraction between those, and there, in between our two molecules, is our dipole. Cool. These next couple are kind of funny. We're using this term induced. Most likely you've heard this in the term or in the form of inducing labor as kind of the human experience. If you induce something, that means you cause it to happen. If you induce labor, you make labor happen. And if you are inducing a current, you are making a current occur. So an induced charge or attraction is one that we made. So for example, we would need to start with a non-polar molecule. So if we look at this molecule of methane, hydrogen, 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 this is a symmetrical molecule. We could say that this is non-polar, but remember it's covered in this sea of electrons, and electrons are slightly negative. If we bring up an ion, for example, a negative chloride, as that negative chlorine comes closer and closer and closer and closer, the electrons around all these hydrogens say, they get repelled away. And so what we end up doing is on this molecule, we induce a partial charge. We actually force the electrons kind of over to one side so that there's now just positives left or a slightly positive void. And so then we see this loose attraction. Conversely, if we were to throw a sodium up there, if we brought a positive up, all of these electrons would shift a little bit towards it and it would become slightly negative, slightly positive. We've induced a polar end and now we've got an attraction between those particles. We could also have an induced dipole-dipole. So for example, if we had water, which is polar, our methane, which is non-polar, if the negative side comes up, it's going to induce just like the ion did, but it's not going to be as much. This doesn't have as big of a charge as a full 1 plus or 1 minus. And so as a result, this attraction is a little bit weaker. It's not as strong in between our intermolecular forces here. The last example that we can start to look at is if we had two non-polar substances. So if we had two molecules of methane, well, is there an attraction here? There could be, right? Again, remember they're covered in these electrons. What could happen is that all the electrons on one side could shift just a little bit. And if they all shifted, all those electrons shifted to one side, become slightly negative. And as a result, all these electrons would shift away, become slightly negative, leaving behind a slightly positive, and we'd start to see a loose attraction. But that's going to be really weak, right? That's not going to be nearly as permanent or as strong as a full partial charge. And that's not going to be as strong as a full-on ion charge. So if you think about kind of the way we've got them listed here, we are decreasing the charges as we go from ion to induced. And as a result, our attraction becomes weaker. As you get closer to things like LDF, these are more likely to be gases at room temperature. Ion dipole, those are in solution or are liquid because those attractions are very, very strong. And so these intermolecular forces play a huge part in the physical properties that we actually exhibit and see in the lab. We'll talk more about how these intermolecular forces start to interact and how we can start to see changes within, but it's good, just brief overview of the different types of forces we can see and why they do what they do.